energy, and sound is also a form of energy. It travels from one point to another in a form of wave. Okay, unlike light, this travels in a form of wave. Now there are various examples of sounds, like when the school bell rings, when the phone rings, so many things. It produces sound. So we'll study in detail how a sound is produced and how a sound propagates from one point to another and how it is heard. Okay. Now over here you can see is sound is a form of energy that travels through material as waves. Now one thing to remember is sound travels through material. It means it requires something for the sound to travel. If there is a vacuum, the sound will not be able to travel. That also we'll study in detail. Now sound travels in a form of wave. That is, sound is a form of energy. Which kind of energy it is? It is a mechanical energy. When a sound is generated at one point, it vibrates, the molecules around that place vibrates, and the vibration continues till we hear in our air. Okay, that is how a sound travels. It travels as a wave from one point to another using materials in between as a medium. Now when I speak, the sound reaches to the camera through the medium. Nothing is there in between. There are air, there are molecules, and that molecule transmits the sound from me towards till the camera. Okay, that is the first basic thing of sound. Now over here you can see is sound is produced by vibration. When sound is produced, like in the first diagram over here, when you hit a drum, the membrane of the drum, the outer layer of the drum, that vibrates. And when that drum, the outer membrane vibrates, what happens? The molecules which are there around, small particles which are there around, that also starts vibrating. And that vibration continues, and the same thing, the vibration is produced in our air also, air drums. And that we can imagine it as a sound of a drum. Now the volume of the sound is very huge. The sound of the drum is very high. It is magnified because of the structure of the drum, of the hollow space which is there in the drum. The sound gets magnified. Similarly in this one, there is a guitar. When you pull the string of the guitar, what happens? The molecules which are there around the string, the molecules, small particles, they vibrate, and the vibration continues till it reaches our air, and we can hear the sound of a guitar. Now the sound also gets magnified because of the hollow space inside this guitar. Now this is a tuning fork. This tuning fork is an instrument. Now what it does is, there are different types of tuning fork which has got different frequencies. So if a certain frequency we will shake a tuning fork, if you hit somewhere, then it starts vibrating, making some very low kind of a sound of a certain frequency. So this also creates sound which we will keep it in our air. We can hear the vibration also. Okay, this is a tuning fork. So sound is produced when the things or the molecules around the object starts vibrating. When I speak, the molecules around my mouth, they start vibrating, and it reaches to another person nearby. Then from there, the person can actually analyze and understand what I am speaking. So sound is produced by vibration. Now in the third step, sound requires a medium. As I've already told you, for anything to vibrate, for anything to produce energy, or for sound to travel, it requires a medium. Sound cannot be produced in vacuum. Sound cannot travel through vacuum. There is one example when a person moves to the moon, and if there is a moon, if it creates a person shocks in the moon, the other person nearby will not be able to hear him because there is no medium. It's vacuum around the person. So it hardly they can contact or talk to each other when they are in outer space because there is no material medium. Now sound requires a medium. There is one experiment over here. This is known as bell jar experiment. Bell jar means this is a jar inside which a bell is kept. This is an electric bell which the electricity is provided by this battery. When the current starts flowing, the bell will ring. There is a round thing over here, it's known as a gong, and this is the hammer of the bell. When we switch it on, the hammer will hit the gong and the sound is produced. Now, what is over here is, this is a vacuum pump. What does a vacuum pump do? It will take out all the air particles outside. All the particles is taken outside. It will make this jar of vacuum. So when this jar becomes vacuum, you will see what happens to the sound which is there inside. Now when we switch it on, the bell starts ringing. Slowly when we take the air molecules outside, the sound of that bell will slowly decrease, or the volume will slowly decrease. When all the molecules when they are there inside, what happens is when the bell is switched on, the molecules around is vibrate. The molecules which are there are vibrate, and it strikes the jar of this one. And the molecules which are there outside the jar also starts vibrating because of the presence of vibration at this place. And we can hear the bell ringing outside also. But when we slowly take the molecules out, there is nothing which vibrates. So when nothing is left to vibrate inside, the sound cannot travel. Okay? So when this is fully made vacuum, the bell will still be ringing, but we will stop hearing the bell because there is no medium to transmit the sound. This is a bell jar experiment which is done by scientists. Okay? When this is made vacuum, slowly the intensity of the sound will decrease, and after some time we will stop hearing any sound because there will be no material over here to transmit the sound. Okay? So for transmission of sound, what we need a medium, any kind of medium like solid, liquid or gas. Sound can travel through three mediums like solid, liquid and gas. This is the jar experiment. Now, in this one, propagation of sound in a medium. In different mediums, like I told you, solid, liquid and gas, how a sound propagates, how a sound travels. This is a small experiment which is there in the book also. I'll explain this to you. In the first diagram, it's quite confusing, but just listen carefully, and in this diagram only, we'll study about what type of wave is generated when a sound propagates from one point to another. This is a metal stripe which is attached to this box. Okay, now when we have a metal, when we vibrate this, what happens? When we push this, it starts vibrating like a scale. If you take and if you do this, it starts vibrating. Okay, it produces to and fro vibration, and from there also sound is produced. Similar experiment is done over here. There is a metal stripe. Now when the metal stripe is kept straight, not in a vibrating position, the air molecules are there like this. These are the air molecules, layer of air. They are stationary, they are not moving because nothing is pushing or pulling them. So they are there. Okay? Now in the next diagram over here, this is the normal condition. Now this is B. Okay. When you start vibrating this, when you start pushing or pulling this, when this is moved forward, when this metal stripe is moved forward, what it does is it pushes the air molecule forward. Okay, it pushes the air molecule forward. When it pushes the air molecule forward, then the air molecule will become pressed, will come closer. So you can see this point, the air molecules are coming closer. Okay, in this figure, the air molecules are brought closer. C is written over here. This means compression of the air molecules to become close to each other. Okay, this compression of air molecules. Now in this diagram, see. Now when we vibrate this, first it was still, then it moved forward, pushing the air molecules, creating compression. Again it moves back to its original position. Okay, it moves back. This metal stripe is over here. When it moves back, now the same kind of pattern is repeated like this. Space is created between the air molecules. Air layers have got some space in between. So some space is created. Here it is compressed, some space is created. Now in this one, when this metal stripe moves backward, okay, first it is still, it moves forward, again comes back to the same position, again it moves backward. When it moves backward, then the air molecules is being pushed backward. When you move like this, the air particles which are there are being pushed backward. So the layers are being rare, or it's also known as rarefied. Okay, so this R is given to this rarefied because this metal stripe is pushing the air molecule backward. Again, when this C comes to the same position, the same kind of layer will be seen. So from all this pattern, what we can conclude is where the air molecules are being compressed. This kind of pattern is seen. This C over here. This is when the air molecules are being compressed. When it is being rarefied, this is the rare pattern. The air layers of the air molecules are far away from each other. When we push push the air molecule, then it will come closer, that is compression. When we take this track backward, it is rarefaction. Okay, compression and rarefaction that happens. Now this kind of wave is generated. Compression, rarefaction, again compression, again rarefaction. So this kind of layer or this kind of wave is known as longitudinal wave. Okay, there are two types of wave. One is longitudinal, another we'll study in the next topic. Okay, this is longitudinal wave. I hope that this is clear. I'll explain it to you again. First, the middle stripe is there. Without any vibration, when you are not doing anything to the middle stripe, the air layers are at same distance. Okay, equal distance to each other. Now, when you are pushing this forward, there is compression because we are pushing the air molecule forward. So this is a layer generated over here. The C is generated over here. Now, when it moves back, again the same first pattern is repeated. Again, when you push this middle strip back, then the air molecule is being pushed back, and this kind of rarefaction pattern is created. Again, when we move forward, again compression is created, move back, rarefaction is created. So this kind of pattern continuously happens till the air molecules reaches our air. Okay, this is the type of wave which is known as longitudinal wave. Now over here. Now, direction of sound waves. How sound travels. Now, if a sound is created from one point from me till the camera, okay, the sound is traveled from the source till the observer. Now, suppose this is a mic, a sound is generated. Now, what is happening over here? The sound generated first is this part. Rarefaction is happening. Then compression. Compression means too many molecules nearby is compression. Then again rarefaction, again compression, again rarefaction. So now we can measure many things over here. Okay, we have to study about many things over here. Now this rarefaction, when we compare it to another wave, this is a transverse wave. When you compare it to another wave, this rarefaction is like this, below. Compression is like this. Again rarefaction, again compression, again rarefaction. Now, distance between one compression to other compression, distance between two compression is the wavelength of that wave. Okay, distance between two compression or distance between two crests. This highest point of a wave is known as crest. This lowest point is known as drop. Okay, crest and drop. So, distance between two crests is wavelength. Okay, and the distance from this line till this one, the height of the wave. This is known as amplitude. Okay? The amplitude is the height of the wave or the distance of the maximum displacement of how much level the wave has lifted, or what is the amplitude. This distance is known as the amplitude. Comparing this, I hope wavelength is clear. It's distance between two compression or distance between two crest is known as wavelength. Now some terms related to wave. These are very important. These are the terms related to wavelength. Wavelength is this one. I have already told you distance between two crests is wavelength. Amplitude is the maximum displacement. You can see the displacement over this side and displacement this side is the same. But this is towards the positive side, this is towards the negative side. So this is amplitude. Okay, this is also known as the amplitude. This is negative side, this is positive side. Now, frequency. Before frequency, there are few terms like time period. Time period for one wave. Now, time period to generate this wave. How much time is taken to generate one wave? This one. This is the time period. Time taken to form this wave. From this point to this point will be the time period. Now, frequency is just reverse of the time period. Frequency is the number of vibrations made by a particle in a medium in 1 second. How many vibrations are made by a particle in 1 second? Okay, that will be your frequency. Now, wavelength I have already told you. Next term is amplitude. Amplitude is all. That is maximum displacement from this line or from the center. Okay, that will be your amplitude. Another is wavelength. Wavelength I have already told you. Wavelength is this one. And the next is wave velocity. Wave velocity is distance traveled by wave in 1 second. Okay, that is known as wave 1 second. That is the wave velocity. Okay, I hope this is clear. Wavelength. This distance is amplitude. Frequency is number of waves generated in 1 second, and just the reverse of the frequency is time definite or that two are the inversely proportional, that I will derive in the next class. Okay, derivation of frequency and time period is also there. I'll make you understand that better in the next class. So for today, up to your day.